Say a few words before you hit pause to try this on your own. They have asked for a unit vector u in the direction from P1 to P2, and we haven't learned how to do that officially yet. I'm going to challenge you to figure that out on your own. I will address it in my solution. Also, notice how in the question you do not see a vector listed either in component form or in IJ form or IJK form in this case. So you're free to do this problem in whichever form you like. It's not specified. However, when we get down to example 5, it's in IJ form in the question, so your answer should be in IJ form. Okay, that's, I don't answer questions during tests, so the question should either tell you what form by example or leave it up to you. Okay, I'm going to do this in component form because it's less to write personally. Okay, so go ahead and hit pause if you want to try it. Here we go. Okay, so the vector P1, P2, we're going to use the head minus tail rule, and I'm going to use component form. So the end minus the beginning. Head minus tail, 3 minus 1. Oh, that's terrible handwriting. Writing on this board is harder than you might think. Okay, 2 minus 0, and 0 minus 1. Okay, so we've got 2, 2, 1, actually negative 1, is the vector P1, P2. Now, this is how long? Let's see. If we use our formula here, negative 1 squared, then we're going to end up with the square root of 9, which is 3. So this vector is 3 units long. How would we cut it back to just 1 unit long? Well, scalar multiplication is going to be your answer here. If it's 3 units long, I need it to be 1/3 as long as it is now. So I'm going to use scalar multiplication to cut it back to just 1/3 of its length. So I'm going to end up with 2/3, 2/3, and negative 1/3 for components in my unit vector. So maybe I could say P1, P2, and put a little hat over it. Now, as a general rule, we just divide the length 3 into each component. So the way they represent that is to say that a vector u divided by its own magnitude is going to be a unit vector u. So there's your rule to take away how to turn a vector into a vector that's 1 unit long but represents the direction of another vector accurately. Okay. So pause now if you're going to try example 5 on your own or if you haven't already done it, and we'll give this a shot. All right, if vector v is 3i minus 4j, and it's a velocity vector, express v as a product of its speed times its direction of motion. Okay, remember speed is magnitude, the length. So the product of its length times its direction of motion. So we need to know its length. So first of all, the length of v is the square root of 3 squared plus negative 4 squared. It's the square root of 9 plus 16, or the square root of 25, which is just 5. So this vector is 5 units long. That's its speed. And we want to express it as a product of its speed times its direction. So we simply have to divide the direction, the speed out of it, and what's left behind, the unit vector. Oh, see, I did the component form and then I started to do IJ form. Don't mix them together. That's bad. So let's erase that. Good for me to make this mistake so you won't make it. So this is going to be 3/5 I minus 4, come on, there we go, 4/5 j, and times, that's its direction, and then 5 is its length. So this is the form they're asking for it in so that you can see both the speed of the motion and the direction of the motion separated out. Okay, let's move on. So here they are showing up finally with how to turn a vector into a vector that is 1 unit long. Okay, so this is a unit vector called the direction of v, and this is true only if v is not the 0 vector, which we've not needed yet. So we'll talk about that when we need it. All right, so this little equation, the length of v times the direction of v, is what it is to express a vector as its length times its direction. So let's see what we've got down here. A force of 6 newtons is applied in the direction of the vector v equals 2i plus 2j minus k. Express the force F as a product of its magnitude and direction. So this is the same question. A force of 6 newtons is applied in this direction. So we want newtons, that's the length, all right? And then its direction. Well, its direction, we have to divide its length out here just to get this down to 1 unit. And this is the same vector we dealt with in the previous problem. So we, actually, not the previous problem, but this one up here, 2, 2, negative 1, had a length of 3. So if we divided, and I'm going to use, here we go, 2i plus 2j minus k. And then we divided its length out. Here's what we would have. 6 is its magnitude, so we don't want to say 6 over 3 is 2. We want to leave the 6 out front, but we have to call this 2i plus, or 2/3 I plus 2/3 j minus k over 3, or 1/3 k. I think I prefer to see the 1/3. It's less confusing. There we go. So 1/3 k. So this is just a convenient form to list a vector in when you're interested in knowing its direction separately from its speed. Okay. Otherwise, you could simply say 6 over 3 is 2 and distribute the 2 and say 4i plus 4i minus 2k. That would be a simplified version, but then you would have to go in and figure out its length separately if you left it in the simplest simplified form algebraically. All right. So more concepts for 3 dimensions that parallel concepts in 2 dimensions. So if we want the midpoint of a line segment that goes from P1 to P2, then we just include the z coordinate in with the 2-dimensional midpoint formula that we were already familiar with. So this is a super simple problem. So our midpoint is going to be 3 plus 7 over 2 for the x coordinate, negative 2 plus 4 over 2 for the y coordinate, and 0 plus 4 over 2. And I've always preferred just to think of this as the average of each of the pairs of components, coordinates, rather than remember this long thing with subscripts and a lot of symbols. So this is going to be 5, 1, 2 is the midpoint excuse me, of P1, P2. All right. And how are we doing? We have a lot more slides. Only a couple more things. All right. So if we want to be able to find the component form of a vector, if they hand us the length of the vector and the direction, and that is all, there's this very nice handy formula. I don't know that they provided this in the book. I think maybe they were expecting you to figure it out, but here I took a picture from a website that would help us to remember doing this in trig class. So when you have the length of the hypotenuse and you need the length of the adjacent, it's hypotenuse times the cosine of the angle with the horizontal. Excuse me. And then if you need the vertical, it's the hypotenuse times the sine of the angle formed with the horizontal, and that gives you the vertical length. So this is just trig class over again. Remember that the bars in our formula here represent the length of v times the cosine of theta and the length of v times the sine of theta. So let's see what problem we've got here to do this with. You may even remember these questions from pre-cal or analysis, whichever class you took. So a jet airliner flying due east at 500 miles per hour in still air encounters, well, if the air was still, it would be moving 500. So here is the vector that represents due east movement at 500 miles an hour. That's vector u. It encounters a 70 mile an hour tailwind, so blowing from its tail, in the direction 60 degrees north of east. So we've got our wind here. That's the v vector. And they've got 30 degrees here because 60 degrees north of east is the 60-degree angle from the x-axis up to the vector. So that's the 60 degrees north of east they're talking about. And it's moving at 70 miles an hour, so it's considerably shorter. And when you combine the two forces, then you add them. And this is the resulting pathway that the airplane flies because the wind is blowing it off course somewhat. So imagine your little airplane sitting here, okay? So there's the the tail and the wings, all right? And this wind, it's trying its hardest to fly this way at 500 miles an hour, but the wind is blowing this way and pushing it off its course to fly along the red vector. And that's a simple vector addition. So we need to be able to express these vectors, u and v, in component form. So u, they've given us the speed and the direction. So technically, we need the length, 500, times the cosine of 0, not theta, degrees, and 500 times the sine of 0 degrees. And that's going to be 500, 0. Now, you probably could figure that out without the trigonometry, but just to show you that it works in all cases. All right, the v vector, the wind, is going to be 70 times the cosine of 60. Now, don't put 30. We want the angle it makes with the x-axis. And then 70 sine of 60 degrees. Okay, and so there's no need to round in the middle. So this is going to be 70 times 1/2, or 35. And 70 times sine of 60 is going to be 35 root 3. It actually didn't tell you how to round, so when it doesn't, don't round. At least put the proper answer in exact form and then round it if you're going to round when they didn't tell you to. Okay, so we need to add u plus v. All right. So we got to keep in mind we need the ground speed and direction of this vector. So first we have to find this vector, and we're going to have 500 plus 35. And we're going to have 0 plus 35 root 3. So it didn't just say what is the vector of the actual path of the airplane. Ground speed would be the magnitude, and direction, well, let's think about the trig. We'd have to do that. So let's do ground speed first. The length of the vector would be the speed of the airplane with respect to the ground. So we're going to have 535 squared and 35 root 3 squared. Okay, and again, this is the proper full form. Well, you can simplify it a little, but you can go to your calculator once you've done it formally and do 538.4. So basically, when you're showing your work, make sure you've got an exact representation and don't just plug it all into your calculator and go straight to this answer if you would like full credit from me. So they said miles per hour, so this is going to be miles per hour. So this wind is actually making us go faster than we had set the plane to go at 500, but then we want to know the direction. So how do you think we're going to find this angle right here? Any particular things come to mind? Well, what we just found here is the horizontal component and the vertical component. The horizontal was 535, and the vertical was 35 root 3. So can we not, to find theta, just look for the angle whose tangent is 35 root 3 over 535, opposite over adjacent. So that's going to be, now there's your exact representation of your answer. No need to reduce, I'm good with that. And then you put it in the calculator and you figure out that that is 6.5 degrees. So we are blown 6.5 degrees off of due east toward the north by this tailwind. So there are our answers, a reminder of how to do vector problems. Okay. By the way, if you want a good example of a problem to understand force questions, look at example 9. I'm not going to go through that one in the video, in the book. Thanks for listening.